In this class, we're going to consider combining graph transformations for trigonometric functions. So if you're not already familiar with individual graph transformations, that is like moving a graph left and right, moving it up and down, flipping it, stretching it, compressing it, all of those individual transformations, and maybe check out those classes first and then come back into this one. In this class today, we're going to look at what happens when you combine multiple transformations, and we're just going to consider some of the things that we need to bring in to handle those different scenarios. So these two examples I've got here have got multiple transformations. So this guy here has got 1, 2, 3 changes to a normal cosine graph. This guy's got 1, 2, 3, arguably even 4 if you split that into 2. So it just makes it more difficult than if you're dealing just with one transformation. But the reason why primarily it's more difficult is if you think about a graph on the XY plane, there are only two directions, right? There's left and right and there's up and down, so horizontal and vertical. But if you've got more than two transformations, so if you've got 3 or more, then at least 2 of those must be acting in the same direction. So to take this one for example, the 2 in front, that stretches the graph up and down the way by a factor of 2, so a vertical stretch. But the 2 on the end also moves the graph up the way by a factor, well, by 2 units. So they're both acting in the y direction, acting on the y coordinates. So we need to think about what they do individually, but also what they do together. And that's what makes these questions more difficult. So we're going to run through these 3 examples. In this one here, we've been obviously given the graph, and we're going to have to identify the formula, the equation, the function that made that graph. So usually with these questions, you'll get a range of values, and the range of values tells you what part of the graph you have to draw. So we're usually just working with 0 to 360 if we're drawing a trigonometric function graph. So what we'll do with this first one is we'll kind of break it down. So we'll identify what the transformations do, and then we might actually draw 2 graphs. Sometimes it's good practice with these to make life a little more manageable to draw maybe part of the transformations on one graph, and then on a second graph draw the other transformation. So for example, we could knock off that +1 and draw the graph of this function, and then after that draw a second graph where we do the +1. So that's what we'll do. We'll start with the graph of y equals -3 sine 2x. So let's think about what those transformations do. So the minus flips the graph, it inverts it, turns it upside down. The 3 stretches it vertically, and the 2 means that it gets compressed horizontally. So there's quite a lot of stuff going on there. The 2 you can also interpret as meaning 2 copies of the graph. So I would recommend for these drawing a reference graph at the side of the original function. So this one is a sine function, just to give you a bit of visual reference, remembering some of the key points. So that's 1, that's -1, and we'll just use that to think about how things are going to get orientated on this new graph. Okay, so let's make a start. They can be quite long, these questions. They're not easy, there's quite a lot going on. You need to keep your wits about you and be careful with how you remap the points. So let's think about some of the key points. So the key points are really these ones here. Where are they going to go on our new graph? Well, if you've got a point at 0 up and down the way, multiplying that by -3 keeps it at 0, so that point will still be at 0. What I think we'll do as well, we'll mark on 360 degrees, which is there. We'll mark on 180, and remember that we need to fit a whole copy of that graph between 0 and 180, and then a second copy here. That's for the 2x part. So the maximum value will be 3, because we're stretching it by a factor of 3, and the minimum value will be -3. Okay, so back to remapping the point. So the point which is at 1, that's now going to become -1, and then stretched even further down to -3. So that point is going to be at -3. It's at 90 along the way, it's now going to be at 45. So we could even put on some more reference points. So that's 180, that's 90, that's 270. So 45 will be halfway along to 90, and that point is at -3. The point here at 0, which was at 0 and 180 along the way, is now going to be at 90 and 0. The point which is at 270 will be at 135. It's at -1 down the way, that's going to get flipped up to 1. In other words, it gets flipped up to here, but then stretched up to 3. So that point at 135 is going to be at 3. So it's up there, and then that final point goes back onto there. So if you just then draw in the points, you should get something that looks like an upside down sine wave and a stretched version of it, because remember we were flipping it and stretching it. And then we just need a second copy of that, so we just draw in a second copy. Oh, let me see if that's right. Yeah, well, it's gone a little bit wonky there, but it's not too bad. So let me just think about that point. Yeah, that's going to go through that point like that, and then turn and go back down like that. So we've got one copy there, and then we've got our second copy there. So that would be that graph there. So what we need to do now is think about the plus one. Well, the plus one just shifts that graph up by 1 unit. So we could actually probably redraw the next part on the same graph. That's probably going to be easier than doing a second graph. Everything's getting moved up by 1 unit, so we just remap those key points and move them all up by 1 unit. So let's mark on -2. That point's now going to be at -2. That guy gets moved up. That point at 3 is now going to be up at 4. That point gets moved up to there. That goes up to there. And you're just basically building up a remapping of all these key points, and then just drawing in the shape of the graph, which should be kind of parallel almost, I guess, in a way to the red graph. So something like that. So we've got that first wave and then that second wave. And if you have to mark on any of these key points, then sometimes you'll be asked to do that. So I think this point here, which that point there corresponds to originally that point is at 270 on a normal graph. Half of that is 135. So that point is at 135 along the way, and it's the very highest point on the new graph, so it's now at 4 up the way. So 135, 4. So this is now the graph of all of that, -3 sine 2x plus 1. So we managed to kind of merge our 2 copies of the graph onto one actual diagram. So not easy, is it? There's quite a lot going on there. They take a bit of practice, these ones. Let's have a look at the next guy. So we've got a cosine function this time. We've got a 2 in front, which is going to stretch it up and down by 2. The -30, that's a horizontal shift, but this is the one that's counterintuitive. That's going to move the graph to the right by 30, not to the left. And then the +2 will move the graph up by 2 units. We'll just draw a little cosine graph over here for reference. So just like the sine graph, but shifted over a wee bit. So maximum value of 1, minimum of -1. And we're just going to manipulate that graph. Let's start again by ignoring the +2 and just drawing the original, the graph with just those transformations, making reference to the original graph. So we'll assume again a range of values of 0 to 360, that would be quite normal. And we'll just go for y equals 2 cos x minus 30. Okie dokie, so just thinking again about where the sort of key points are going to end up. Right, so the key points really are this first point here, this point here, that one, and that one. Those are the points we're trying to work with. So that first point there, which is at 1, is going to be stretched by a factor of 2, so it's now going to be at 2, and it's also going to be moved 30 units to the right. So we'll maybe just put on our references again. So that's 360, that's 180, that would be 270, and that would be 90. And we'll just say that that there is 2, and that there is -2, because we know it's going to be between 2 and -2 this time. So that point is now at 2 up the way, but it's at 30 along the way, so it's going to be somewhere there. This point here, this point here is now going to be at 120, because it's 90 plus 30. But it's still going to be on 0, because 0 times 2 is still 0 up and down the way. Okay? The point which is at -1 is now going to be at -2, but instead of being at 180, it's now going to be at 180 plus 30, which is 210, just somewhere there. This one would also get moved over. This one at 360 would now be at 390. That's outside our range, but you can still mark it on, but just don't draw the graph past 360. So our graph is going to come from here. Be slightly careful with this point, because remember that that point at 1 was actually the peak, like the turning point. So it's not a case that the graph comes down to that point, it's actually peaking at that point. So it's actually going to go up a little there before it starts to turn down. It's going to go through that point. The shape should be the same. Stops at 360, which is a little lower than that point there, and then the rest of the graph to 390, to that maximum point, would be beyond the range. So you only really need to draw it up until that point there. Okay, so that's basically that graph there. To get the +2 part on, we're now just going to take that graph and move it up by 2 units. So this is actually quite straightforward. I would say that because I've run out of space here, I'm going to draw on another graph. But because you're going to be moving it up by 2 units, the lowest value, -2, is now going to be up at 0. The highest value, 2, is now going to be up at 4. So you could maybe draw your graph looking a bit more like this, where the x-axis is quite low down, because all of the action in this graph is taking place above the x-axis. So we'll mark that on as 4, we'll mark that on as 0, and then we're just basically mirroring the graph at that point. So it's just going to be identical to this one here. That point there we could maybe map on, so that's going to be at 210 along the way, but it's now going to be at -2 plus 2, because we're now adding on the 2 to take it up to 0. So it's going to look basically like that there. And then the graph shape just goes down through there, goes back up and stops somewhere about there. And then again, if you need to mark on points, so that one was 210 along the way and 0 up and down the way. This point here, for example, this guy here, was at 30 along the way and 4 up and down the way. So sometimes when you draw these graph transformations, you'll be asked to mark on some of the key points. Okay, so that's what's going on there. Not easy, quite a lot of stuff going on. Let's take a look at the last one. So sometimes with these, where you're given the graph, if you're dealing with a sine or a cosine, it can be quite difficult to know which one it is, because remember, sine and cosine are the same graph, just moved over by 90 degrees. So I think we can assume this one is a cosine. So we're going to say this started off life as the graph cos x, and then we need to figure out, well, what's different between that graph and a normal cosine graph. So let's go ahead and just put down a normal cosine graph for reference. So it normally goes between 1 and -1. One of the features of a graph like that is that because the maximum is 1 and the minimum is -1, that means you've got a vertical range of values of 2. So in other words, the difference between 1 and -1. But notice that on this graph, there is a vertical range of values from 3 to -5, which is a difference of 8. That tells you the graph has been stretched by a factor of 4, if I can get my fingers right. Yeah, 4. So that tells you that instead of being cos x, it's going to be 4 cos x. But if you took a graph of cos x and stretched it by 4, that value would be 4, and that would be -4, just by multiplying those numbers by 4. But that's not what we've got. So they've done the stretching by 4, but we've also, something else has happened here, because it's now 3 and -5. Well, you can see that's just been moved down by 1. So 4 goes down to 3, -4 goes down to -5. Moving the graph down by 1 is achieved by putting a -1 on the end like that. So that's how we can start to figure out the formula. Notice as well, we've got one cycle of the graph here, but it's happened in 0 to 180 degrees. That's not normal, is it? Because this endpoint should be 360 degrees. So what's happened there? Well, the graph's been squished, compressed, to use the proper word, by a factor of 2. So that means that we have to put, a 2 in there to make it cos 2x. And if you carry that graph on, you would get a second wave in the range 0 to 360. So that is our formula. Y equals 4 cos 2x minus 1. So if you're working this topic, which is a great topic to work in trigonometry, working with the graphs, it gives you a really good sense for the trig functions, and these are pretty common question types. If you are doing this, I would recommend trying both types. So ones where you've got to draw the graph, especially with multiple transformations, and the ones where you've got the graph and you've got to make the formula. Going both ways really kind of adds to your understanding, kind of fills out your skill set. A lot going on here, not easy, they are difficult. I would recommend as well maybe using a graphing utility to help you with these. So you can use an online tool like Desmos or Graph Sketch, or there's one called GeoGebra. There's a whole bunch of them online that you can use to help you check whether your graphs look right or whether they've gone horribly wrong. Quite a skillful topic, this one, requires quite a bit of practice. So make sure that those examples kind of make sense to you, and then definitely check out a few practice questions.